Hi guys, this is Dr. Manjunath Chennapgod from Anveshana Academy, Bangalore, India. Dear students, in the previous video, we were discussing about what is Otto cycles, how the Otto cycle came into existence, what are the important operations which are explained by Otto, Nicholas Otto. Okay, so what are the important, how it works, that Otto cycle, how it works, what are the important process it is having, that we have discussed in detail. So now I will move towards next topic. So next topic, again in continuation with Otto cycle itself. What is the next topic that you can see? Expression for an air standard Otto cycle efficiency. Dear students, we are going in this class, we are going to determine the efficiency expression or equation for Otto cycle. That is a air standard cycle. So Otto cycle, the efficiency equations we are going to derive today. Fine. Okay, dear students, as we discussed in the previous class, that too working of Otto cycle, as I told, there are four important processes. One is adiabatic compression, constant volume heat addition, adiabatic expansion, and constant volume heat rejection. So this process play a very important role in deriving the expression for Otto cycle efficiency. The first one is process 1, that two process 1, that is nothing but what? Process 1 to 2. The name of the process is 1 to 2, that is nothing but what? Adiabatic compression. So you can, dear students, in detail we discussed. I will start with point 1. Okay, so from point 1, that is BDC to TDC. When the piston moved from BDC to TDC, what happens? The whatever the air fuel mixture it is there inside the cylinder, right? It will be get compressed. That process we can call it the adiabatic compression. Why it so? Why it is adiabatic? But there is no heat transfer. There is no heat transfer. That process we can call it the adiabatic process. In this process, what actually happening now? Piston is moving. Just a minute. Okay, the piston is moving from BDC to TDC, hence compression will take place, but there is no heat transfer, hence Q equal to 0. When piston moved from point 1 to point 2, temperature as well as pressure of the air fuel mixture gets increased. That means what? When the piston moved from BDC to TDC, volume is changed from V1 to V2. That means what? Volume is decreased. Here you can see here now, dear students, when the piston moved from point 1 to point 2, volume decreases, whereas temperature and pressure increases. Hence pressure increased from P1 to P2 and temperature increased from T1 to T2, whereas volume decreases from V1 to V2. Okay, the same thing I have written it here now. When it is a adiabatic process, as I told, Q equal to 0. Then when the piston suddenly it is compressed the air fuel mixture, right? What actually happened there? Temperature and volume varies. Temperature as well as volume varies. That ratio we can give in terms of T2 by T1 is equal to V1 by V2 to the power of gamma minus 1. So as the air fuel mixture is get compressed, suddenly what happened? The temperature also changed, volume also changed. The variation of temperature versus volume, that can be written in terms of an equation. That equation is T2 by T1 is equal to V1 by V2 to the power of what? Gamma minus 1. That I will call it as a equation number 1. Equation number 1. Once the piston reaches from point 1 to point 2, then what will happen now? Compression is done. Adiabatic compression is done and we got an equation. That equation also we written, and that equation we called it as a equation number 1. Okay, now I will move towards next process. What is that next process? That is process 2. That is nothing but what? Process 2 to 3, that is nothing but constant volume heat addition. So once the air fuel mixture is at this particular point, that is it gets compressed, piston is at TDC. At that moment, what you are going to do? With the help of spark plug, with the help of ignition, what we are doing, we are going to supply certain amount of heat. The amount of heat supplied is represented by what? Qs. Okay, so you are supplying heat. At what condition? You can see here now, that is very important in the Otto cycle. You are supplying heat to the engine at point 2 to 3 where volume remains constant. I mean, at constant volume, what you are doing, you are supplying certain amount of heat. That heat supplied, some author they will take Qs, some author they will take Q1, some author they will take QH also, but you be familiar. Okay, now what I will do, I will take heat supplied as a Qs. Okay, in the second process, what you are doing, you are supplying heat at constant volume. Then what happens when you are going to add heat to the engine at 2 to 3, then what happens? Temperature increased from T2 to T3 when we are going to add a heat, right? Once the heat is added, temperature increase from T2 to T3, then pressure from P2 to P3, P2 to P3. So that you have taken here now. But what we are doing now, you are supplying certain amount of heat. Then how much amount of heat you have supplied? That can be calculated with the help of an equation. What is that equation? We know already, general equation. What is that? Qs is equal to m into, it is a constant volume process, hence we are taking Cv, specific volume. Okay, Cv, what are the two temperatures here now? Change in temperature, what is that? T3 minus T2. So T3 minus T2. How much amount of heat supplied in this particular process? That is 2 to 3. That can be calculated with the help of an equation. That equation is Qs is equal to m into Cv into T3 minus T2. So the same thing I have written it here now. So therefore, heat supplied to the engine at 2 to 3 at constant volume, at temperature T2 and T3, pressure P2 and P3, I can express that in terms of an equation. That heat supplied, I can write it in terms of equation. That is Qs is equal to, so that is, you can see here, dear students, Qs is equal to m into Cv into T3 minus T2. What is m? Mass of the fuel what you have taken. Cv is a specific volume. Okay, specific volume. Specific heat at a constant volume. Cv means specific heat at a constant volume. Specific heat at constant volume, at volume process that you have to keep. One more will come, Cp also will come, specific heat at constant pressure, that we will discuss in detail next upcoming diesel cycle. Cv into T3 means what? Temperature of the temperature at a particular point 3, that is T3. Then T2 means what? Temperature of the gas at point 2, that is T2. So this I will call it as a equation number 2. This I will call it as a equation number 2. Now what have we done here now? The air fuel mixture is get compressed from 1 to 2. Then for that air fuel mixture, compressed air fuel mixture, what you done? You supplied heat at point 2 to 3. This is done now. Now second process is done. Now I will move towards third process. What is the third process? That you can see here now, dear students. What is the third process? Third process, once heat is added to the air fuel mixture, then what will happen? Sudden expansion will take place. Isentropic expansion will take place, but there is no heat transfer during that process. That we can call it as adiabatic expansion. Then what will happen now? When you already initially the piston, now it is received after the compression, the piston is at particular point TDC, then volume become constant. At that moment, with the help of spark ignition, you are going to supply certain amount of heat. Because of that heat ignition, what will happen? Sudden explosive force is going to exert, because sudden there is a rise in the pressure, rise in the temperature. Then what will happen? That that fuel mixture, when it started to burn, right, it becomes hot gas. That hot gas is going to exert pressure over the surface of the piston, hence the piston will start to move from TDC to BDC, hence expansion will take place. But there is no heat transfer from system to the surrounding during expansion. That process we can call it as a adiabatic expansion. When it is expansion, right, then what happens now, dear students? Now you are at this particular point, right? When expansion takes place, piston will move from TDC to BDC, hence it becomes from point 3 to point 4. 3 to 4 is nothing but what? Adiabatic expansion. But here there is no heat transfer, that is equal to 0. For that purpose only we are going to call it as a adiabatic expansion. But here, dear students, we can see here now, during expansion, volume increases from V3 to V4 and temperature decreases from T3 to T4. So the same thing we have written it here. Volume, what actually happens here now? When the piston expands, volume increases from V3 to V4. See here now. Here is the volume. This is a less volume. At V3, volume is less. When it expands, the volume is increased. That to V4. So hence the volume is increased from V3 to V4, whereas temperature drops from T3 to temperature drops from T3 to T4 when the piston moves from TDC to BDC. Then that I can, whatever the concept I told, right, that I can express in terms of an equation. How to express in terms of equation? As I told, during expansion there is no heat transfer at all, hence it is adiabatic process or adiabatic expansion. That I can show it in terms of equation. How? That is Q equal to 0. Q equal to 0. Then whatever, when the sudden expansion takes place, right, there is a change in temperature and volume. The variations in the volume and temperature can be expressed in terms of an equation. What is that equation? So T3 divided by T4. This is what? T3 T4, T3 divided by T4, T3 divided by T4 is equal to V4 divided by V3 to the 4 of what? Gamma minus 1. The variation of temperature versus volume can be expressed in terms of an equation. That equation is T3 by T4 is equal to V4 by V3 to the 4 of what? Gamma minus 1. That equation I will call it as a equation number 3. That equation I will call here it as a equation number 3. Now the process 3 is over. Now I will move towards next process. What is that next process? That is process 4 to 1. That is nothing but what? Constant volume heat rejection. Once the work is done, whatever the hot gases which is present inside the cylinder, right, that has to come out from the cylinder. Then only we can supply fresh air fuel mixture to the engine for a next cycle. So what we have to do? We have to remove the exhaust of hot gases which is present inside the cylinder. That how we are going to remove? We are going to remove that hot gases at a constant volume. That is nothing but what? Heat rejection at constant volume. That is nothing but what? Process 4 to 1. That you can see here now, dear students. Okay. What happens now? Now point 4 you reached, right? Then you are moving from point 4 to 3. That means what? Piston already it reaches the BDC. It reaches the BDC during the expansion. Fine. Now what we will do? We are going to open the exhaust valve. Then what happens? Whatever the hot gases which is present, right? Just a minute. I will show here. Okay. Fine. Now you can see here. 1 minute. Okay. 1 minute. Fine. So now when it is a hot gases, right, now assume that at the end of the third process, adiabatic expansion, piston position is at BDC. Piston position is at BDC. At that moment what we are going to do? We are going to open the exhaust valve. When you are going to open the exhaust valve, right, whatever the hot gases which is present inside the cylinder, that will come out. That means what? Heat is getting rejected from system to the surrounding at constant volume. The volume remains constant. Heat is rejected. For that process only we can call it as a constant volume heat rejection. Then how much amount of heat is getting rejected? Again, that can be calculated with the help of an equation. Now we are at a particular point. 1 minute. We are at a particular point now. 4 to 1, right? At 4 to 1, what actually happening now? Heat is getting rejected. So 4 to 1. At 4, what is the temperature? We are having T4. At point 1, we are having temperature T1. These are the two temperature difference here now. Now heat is getting rejected. That heat, how much heat is getting rejected? That we can calculate with the help of an equation. What is that equation? We know already. General equation is heat rejection. That is QR is equal to mass of fuel mass of hot gases into specific heat of gas at constant volume into change in temperature. What is the change in temperature here now? T4 by T1, because T4 is higher here, so I will write it here T4 minus T1. This is nothing but what? Amount of heat rejected during the fourth process, that is constant volume heat rejection. Then how to write the equation? So therefore QR is equal to M into CV into T4 minus T1. That I will call it as equation number 4. That we will call it as equation number 4. And one more thing, dear students, that you can see one more diagram. TS diagram also you can see here now. So TS diagram, temperature variations versus entropy we can express now. So what is our process? 1 to 2 is what? 1 to 2 is a compression. That means what? Isentropic compression. There are two isentropic process. One is isentropic compression and isentropic expansion. What is isentropic compression? Sudden compression from point 1 to 2. Once you compress, then what we are going to do now? Later, we are going to supply certain amount of heat. That heat supplied can be shown in the TS diagram also. How we can show? At 2 to 3, what we are doing? At process 2 to 3, you are supplying heat, right? That heat supplied represented as at 2 to 3 like QS. QS represent what? Amount of heat supplied during process 2 to 3. That is what? You are supplying heat. That means what? The sign is inside the cycle. That means what? Heat supplied. Once it done, then what happens now? Sudden heat is supplied. Once heat is supplied, then what happens? Sudden expansion will take place. That expansion, how it is going to take? From 3 to 4. From 3 to 4, what will happen? Sudden expansion is going to take place. That also we can show it in the TS diagram. Once expansion is happened, thereafterwards, what will happen now? The piston will be at BDC itself. We are going to open the exhaust valve. Hence, the heat is going to reject. That heat rejection we can show from 4 to 1. From 4 to 1. So heat is getting rejected. Now the sign is outside. That means what? Heat is removed from system to the surrounding. That heat removal or heat rejection can be represented with a notation that is QR, where heat supplied is QS. Okay, this is about what? Working of TS diagram. Just a minute. One minute. Fine. Now, these students, so now what is process 1 to 2? Process 1 to 2, what you can say? Isentropic compression or adiabatic compression. What is 2 to 3? 2 to 3 is, what is 2 to 3? Heat addition at constant volume. 2 to 3 is heat addition at constant volume. Then what is 3 to 4? 3 to 4 is isentropic expansion. That is nothing but 3 to 4 is isentropic expansion. What is 4 to 1? 4 to 1 heat rejection at constant volume. 4 to 1 heat rejection at constant volume. That you can see. Heat rejection at constant volume, that is 4 to 1. Okay, this is what? The Otto cycle. This is nothing but what? Otto cycle. Now, with the help of this Otto cycle, we can design the engine by calculating the engine efficiency, engine power, okay, engine emissions, like that, different parameters. Now, process 1, 2, 3, 4 we have discussed. With the help of the data, what we got, right? We got some equations. Equation 1, 2, 3, 4. Like that, we got some equations. With the help of these equations, we can calculate the efficiency of the Otto cycle. How it is, that you can see here, dear students. Now, so now what we have to do then? Later, once you got all 4 equations during 4 processes, with the help of that 4 equations, we can calculate the efficiency of the Otto cycle. How it is, that you can see here now. We know already, dear students. What is the efficiency formula? Generally, we know efficiency of the engine, or efficiency is nothing but what? Work done by the engine to the heat supplied. Generally, we know what is efficiency. Efficiency is equal to output by input. It's a general formula. What is the output from the engine? Work done. What is the input for the engine? Heat supplied. So therefore, work done per an so therefore, efficiency for an engine is ratio of work done to the heat supplied. So therefore, efficiency of an air standard Otto cycle is work done to the heat supplied. So how to write the work done equation? Dear students, in the previous class itself I told, with the help of first law of thermodynamics, we can write the equation W is equal to Q, but net work you have to take, that how I can take amount of heat supplied minus amount of heat rejected. So therefore efficiency is equal to work done is nothing but heat supplied minus heat rejected to the heat supplied. So therefore what I can write now, so efficiency is equal to what, how I can write it now, work done is qs minus qr, qs minus qr, sorry, qs minus qr divided by what, heat supplied, that is what, qs. The same thing I have written it here now, heat supplied minus heat rejected to the heat supplied. So therefore I can write it in terms of notation, that is efficiency of air standard cycle is equal to qs minus qr divided by qr. This is the main equation to calculate the efficiency of the Otto cycle. So dear students, we know what is qs and what is qr and what is qr. This is what, dear students, you make it as a qs, small correction, it is a qs. Okay, now this I can write now, this I can write, how I can write it now, so efficiency is equal to 1 minus qr divided by q, yes, the same thing I have written it here now, efficiency is equal to 1 minus qr divided by qs. Dear students, we already know what is the value of qr and qs, where during heat addition and heat rejection we got an equation of what, heat supplied and heat rejection. What is the heat supplied equation, that you can see here now. What is the heat supplied? So heat supplied equation is what, qs is equal to m into cv into t3 minus t2, one equation, that is qs. Then qr is nothing but what, qr is equal to what, mcv into t4 minus t1. This equation we got already, the same equation I am going to substitute here now, 1 minus qr, what is the qr, mcv minus t4 minus t1, t4 minus t1, because heat getting rejected, you can take it here now, heat rejection, that is qm into cv t4 minus t1 divided by heat supplied, where you supplied the heat, this particular point, t3 minus t2, that is nothing but what, you have to consider amount of fuel also, air fuel mixture or hot of air fuel mixture, what you have considered, that is m into cv into t3 minus t2. So therefore how I can write it now, dear students, you can see here now. So what I have done, you can see here now, efficiency is equal to 1 minus, what is the value of qr, qr is equal to m into cv into t4 minus t1 divided by m into cv into what to write now, t3 minus t2. Then one thing you have to see here now, both m get cancelled, cv will get cancelled. So therefore what we can get, efficiency is equal to 1 minus t4 minus t1 divided by t3 minus t2. So the same thing I have written it out. So therefore efficiency is equal to, efficiency of an air standard cycle, that is Otto cycle, is equal to 1 minus t4 minus t1 divided by t3 minus t2, that I have written it here now. Once it done, small changes I will do here now, dear students. The same above equation I will modify and I will write it like this, 1 minus what I will do, I will try to take the t1 outside here now. So therefore what I can write, t4 divided by t1 minus 1 into t1, the same equation. What I am doing here now, I am taking t1 outside in the numerator side. Fine. Next, similarly what I am doing, I am taking t2 outside in the denominator side. That is nothing but what, t3 divided by t2 minus 1 t2. This is what, same equation I have written in other form. That equations you can see here now. How I have written equation, 1 minus t4 minus t1 minus 1 into t1 divided by what, t3 by t2 minus 1 into t2. Then that equation I called it as a equation number 5. 4 equations we already got from the process. Now after substituting the values in the efficiency formula, we got an equation. That equation is t1 minus t4 by t1 minus 1, t4 by t1 minus 1 divided by 1, t3 by t2 minus 1 divided into t2. This is what, equation number 5. Okay, dear students, we have to, this is, you have written it as an equation number 5. Fine. Now you go back to the equation number 1. What is the equation number 1? While adiabatic compression, variation of temperature with volume, we return one equation. What is that equation? That you can see here now, dear students. What is the equation? Just a minute. Okay, now you have written the equation here now. What is that equation? What What is that equation? T2 by T1 is equal to V1 by V2 to the power of gamma minus 1. So that you called it as equation number 1. So I will use that equation number 1 for further calculation. So that what I have done, I have taken equation number 1 here now. What is that? T2 by T1 is equal to V1 by V2 to the power of what? Gamma minus 1. Okay, dear students, that is very important here now. During Otto cycle, what we done? We supplied heat at constant volume and rejected heat at constant volume. Then that also need to consider here now. So now how the heat is added at 2 to 3, right? So what is the volume now? This is what pressure at horizontal vertical axis, at horizontal volume is there. Sorry, at horizontal axis volume is there. Now you draw a line vertically, then T2 and T3 they are going to lie at the same point in the x axis, that is horizontal volume axis. Okay, that means what? V2 is equal to V3. That means what? At point 2 and 3, V2 is equal to V3, constant volume process. Similarly, you can see heat is also going to reject at 4 to 1. Again, you can draw a vertical line, then that line is going to touch the horizontal axis, that is volume, where volume V4 and volume V1 is they are going to intersect at a particular point 1. That means what? So what we can say? V4 is equal to V1. They are going to lie at a same point. That means what? V4 is equal to V1. These two points we are going to get it from the Otto cycle itself. The same values I am going to substitute here now. How I am going to substitute? That you can see here now, dear students. 1 minute. Huh? Okay, fine. Now, so then same, what is the V2? We know already. What is that? We know that V2 is equal to V3 from the diagram, V1 is equal to V4 from the conditions. Now what I can do here now, that you can see here now. So therefore T2 by T1, what is the value of V1? V1 is equal to what? V4. What is the value of V2? V2 is V3. I will substitute V1 and V2 in the above equation here now. In this equation, what will happen now? So therefore T2 by T1, wherever V1 is there, right? Just a minute. Okay, T2 by T1 is equal to V1. What is the value of V1? That is V4. I will write it here V4 divided by V2. What is the value of V2? That is V3. So therefore V4 by V3 is V3. I have written. Then to the power of what? Gamma minus 1. To the power of gamma minus 1 I will write as it is. Then that equation I will call it as a equation number 6. So T2 by T1 is equal to V4 by V3 to the power of what? Gamma minus 1. This we got. That I call it as equation number 6. Now I will go to the further calculations. What is that further calculations? Dear students, you can go compare 6 and 3 equation. What are the 6 and 3 equation? You got already. Okay, what are the 6 equation? What is the 6 equation? That is what? T2 by T1 to the power of this one. And third equation, what is the third equation? You can see now T3 by T4. So what is the value of V4 by V3 to the gamma minus 1? That you have calculated now. So V3 by V4 to the gamma minus 1 value is nothing but what? T2 by T1. So the same thing I am going to substitute here now. So T3 by, that is nothing but equal, right? So therefore T3 by T4 is equal to T2 by T1. You understood or not? So I will write once again. I will write it here now. Once again. I will write the equation number. 1 minute. What is that equation? T3 by T2. What is that? That equation. 1 minute. T3 by T4 is equal to T3 by T4. Sorry. Okay. T3 by T4 is equal to V4 by V3 to the power of what? Gamma minus 1. This is the equation. Fine. Now what you have calculated? This is what? Equation number 3. Yeah, it's your equation number 3. We know what is the equation number 6? That 6 also you can see here now. What is the equation number 6? That is what? T2 by T1. That is 1 minute. What is that? T2 by T1 is equal to, you got the value V4 divided by V3 to the power of what? Gamma minus 1. This is what your equation number 6 that you can see here now. Equation number 6 is what? V3 by V4 gamma minus 1. Alright, that is the equation. Now you can see now what is the value of V3 by V4, that is T2 by T1. So then what I will do, instead of this I will compare these two equations and I will rewrite the equation. So therefore what happens now? What will happens now? You can see here now. So therefore T3 by T4 is equal to, what is the value of V4 by V3 to the power of gamma minus 1? That is nothing but what? T2 divided by T1. So I got the equation as T3 by T4 is equal to T4, T3 by T4 is equal to T2 by T1. This equation I can rewrite like this also. How I can write? T4, 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 this I will take this side. T4 divided by T1 is equal to, what I can write now? Now T3 divided by T3, this I will send it this side. This I will take this side, T4 by T1. Then this I will take at this particular point. That is nothing but T3 by T2. So the same thing I have done it now. T4 by T1 is equal to T3 by T2. That equation I will call it as equation number 7. Now you substitute this 7 equation in 5. What is the 5 equation? That is our efficiency, right? If 7 equation is nothing but what? That's our efficiency equation. That is what? 1 minus T4 by T1 minus 1, T1, that is T3 by T2 minus 1 divided by T2. Then what you have to do? You have to substitute the value of what? What value you have to substitute here now? That you can see here now. 1 minute. Fine. What you have to do now? 7. Whatever the 7 is there, right? Now, what is this now? Once again, I will write once again, I will write the equation 5 here. T4 1 minus T4 by T4 minus T1. That is efficiency is equal to 1 minus T4 by what is that equation? T4 by T1. T4 by T1 minus 1 into T1, T1, okay. This divided by, this is actually 1 minus like this, efficiency 1 minus. The next T3 by T2 minus T3 by T2 minus 1 into T2. Is it right? Okay, T3 by T2 minus T. So now from this equation, what is the value of T4 by T1? Here you need to substitute. T4 by T1 is what? T3 by T2. I will substitute. So therefore efficiency is equal to 1 minus, what is T4 by T1? T4 by T1 is nothing but what? T3 by T2. I will write it here now. T3 by T2 minus 1 into T1. Similarly, what I will write now? T3 by T2 minus 1. So it into T2. Then what happens now, dear students? Here now, at the denominator side and numerator side, you can see T3 by T2 minus 1, T3 by T2 minus 1 get cancelled. Then remains what? Efficiency is equal to 1 minus T1 by T2. The same thing I have written it here now. So T3 by T2 minus 1 into T1, T3 by T2 minus 1 into T2. Therefore, what actually going to happen here now? This term and this term, they are going to get cancelled. The remaining term is what? 1 minus T1 by T2. That we can call it as equation number 8. That we can call it as equation number 8. Now one thing you have to remember, dear students, when the compression takes place, right, that compression ratio we can write. How to write the compression ratio equation? That is RC is equal to V1 by V2. So in the from the equation number 1, we already know equation number 1 is what? That equation number 1 I will come here. What is the equation number 1? What is equation number 1? Just a minute. What is equation number 1? That is what? T2 by T1, that is V1 by V2. What is compression ratio? Compression ratio is V1 by V2. So wherever V1 by V2 is there rated, that is nothing but what? RC. So the same thing I am going to write it here now. So therefore what I can do here now? Wherever, okay, T2 by T1 is equal to V1 by V2. That is T2 by T1 is equal to what? RC to the power of gamma minus 1. Okay. Now it is T2 by T1. I can write T1 by this equation, I can write like this also, vice versa. I will take T1 numerator side, T2 I will send it to denominator side. That is nothing but T1 by T2 is equal to, if it's so, how I can write it now? 1 divided by Rc to the power of what? Gamma minus 1. The same thing I have written it now. The same T2 by T1 I can write it in another way, that is T1 by T2 is equal to 1 divided by Rc to the power of gamma minus 1. So therefore what I can write now? T1 by T2 is equal to 1 divided by Rc to the power of gamma minus 1. That equation I will call it as equation number 9. Now what I will do? I will substitute equation 9 in equation 8. I will substitute, just a minute. Now what I will do? I will substitute this equation in equation number 8. What is that? Now, so efficiency of air standard cycle, is equal to 1 minus, what is the value of T1 by T2? The T1 by T2 value is, you can see here, T1 by T2 value is 1 divided by Rc to the power of what? Gamma minus 1. So 1 minus 1 divided by Rc to the power of gamma minus 1. This is the a standard equation for what? Otto cycle. At the final, what you can do? This is the final equation. So therefore, efficiency of Otto cycle is 1 minus 1 divided by Rc to the power of what? Gamma minus 1. Okay. What is Rc here now? Compression ratio. This is what? Constant. Okay. So now, so therefore, what you can write now? You can write the final equation in this fashion. That is, efficiency of air standard cycle or Otto cycle is 1 is equal to 1 minus 1 divided by Rc to the power of what? Gamma minus 1 for the Otto cycle. This is the expression for the Otto cycle. Dear students, hope you understood this derivation well. Okay, understood well. Thank you for your support. And dear students, here with a request you please subscribe my channel, do comment and say, and your support will help me a lot. So please do subscribe my channel. Thank you.